Okay, section 9.2 is on polar equations and their graphs. So we'll just jump right in. First one here, we are asked to graph a polar equation. Theta is equal to 5 pi over 4. Okay, so remember from last class, if we have something in polar form, we usually have two variables. We have both r and we have theta. Okay, so if we want to graph theta is equal to 5 pi over 4, it might not look exactly like what you have pictured in your head. So anytime we want to graph something and we don't know what it looks like, we would start with a chart of values, whether it's in polar form or rectangular form, right? What we did with sine, cosine, tangent, we made a chart of x and y values. Here, what I'm going to do is make a chart of r and theta values. Then we'll plot all of those points on our graph and see what they look like. And then you guys will think like, aha, that's pretty much what I thought it was, but maybe a little bit of a surprise in the end there. Okay, so what I know is that theta is equal to 5 pi over 4. So no matter what r is, theta is 5 pi over 4. Okay, so no matter what r is, theta is 5 pi over 4. So now what we're going to do is just pick some values for r. So I picked 2, 1, 0, -1, -2, and look, I have an extra one. We'll call that -3. Okay, so what we're going to do is plot all of these points and connect them on a graph and see what 5 pi over 4 looks like. Theta is equal to 5 pi over 4. Okay, so the first point here we have is 2, 5 pi over 4. So 5 pi over 4, this is equal to pi plus 1/4 pi, or pi plus pi over 4, so we can visualize that. So in order to plot this point, the first thing we do is draw in the angle 5 pi over 4. So that is 1 pi plus 1/4 4. This is 5 pi over 4. Okay, then we want to go a distance of 2 out from the pole out to our point. So our pole is our origin. We're going to go a distance of 2 out. This is the point, 2, 5 pi over 4. Okay, so now let's plot our next point. So the first thing we do is draw on 5 pi over 4. That's already there for us. Now we'll go a distance of 1 out. So this is the point 1, 5 pi over 4. The next one, 0, 5 pi over 4, that goes a distance of 0 out. So I would guess that most of you, when I asked you to graph theta is equal to 5 pi over 4, what you have pictured in your head is this part, right? Here's r is 0, 1, 2. If we were to continue out 3, 4, we would actually include all of these points. Okay, the part that maybe some of you might not have thought about were these negative r values. So we need to plot these in. Okay, so remember, if we have negative r values, we want to go this distance on the opposite ray. So the opposite ray looks like that. And so when r is -1, we go a distance of 1 away on the opposite ray. When r is -2, there's our point. When r is 3, etc. Okay, so if we're asked to graph 5 pi over 4, theta is equal to 5 pi over 4, it's actually this entire line and not just this terminal ray from that angle, okay? Any questions on that? Okay, so there's another method of graphing a polar equation, and that's by converting to rectangular form. Okay, so if we want to convert this to rectangular form, we're starting with theta is equal to 5 pi over 4. There's a little bit of a trick here. So our goal is to get this in terms of x and y. That's a rectangular form. So the trick here when we see theta is I can take tangent of both sides of the equation. And then tangent of theta, we know from last class, that's equal to y over x. And then on the right side here, tangent of 5 pi over 4, that's equal to 1. The last thing we should do here to get in a rectangular form is we like to usually put things in slope-intercept form or in y equals form. So I'll multiply both sides by x and I get y is equal to x. Okay, so this is just a line with slope of 1 and y-intercept of 0, which is exactly what we got up here. Okay, so if you're ever asked to graph these on a homework or on a quiz, or if you did have these on a test, you could do these in either way. Either we can make a chart of values or we can convert to rectangular form. They both should match. I would encourage those of you moving on to higher math classes to just practice both ways and make sure they look the same. Any questions on this? Okay, I got 2 more real quick ones for you guys today. Any questions? Okay, the next one we'll graph r is equal to 6. Okay, so again, anytime we want to graph something, we have no idea what it looks like, we can make a chart of values. So in polar form, we have 2 variables, r and theta. So we'd want to make a chart of r and theta. This tells us that no matter what theta is, r is 6. So we'll just put 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6 down here. So now we can pick any value of theta, and no matter what theta is, r is going to be 6. So 0 degrees, 45 degrees, 90 degrees. We can pick anything at all, 135 degrees, 180. 225, dot, dot, dot. Okay, let's plot these points and hopefully this should make sense to you. Okay, if r is 6, we're looking at all of the points that are a distance, right? R tells us our distance from our pole out to a point. We're looking at all the points that are a distance of 6 from the origin. So if all of our points are a distance of 6 from the origin, what shape do you think I'm going to end up with? A circle, yeah. So let's plot these. So here's 6, 0, here's 6, 45, here's 6, 90, 6, 135, 6, 180. And you can see all the points that are a distance of 6 away form a circle. Okay, so that one hopefully should be obvious. The other way of doing this is by converting to rectangular form. So if we have r is equal to 6, the trick here is to square both sides. If I square both sides, I get r squared is equal to 36. Then I can make the substitution we saw from last class that r squared is equal to x squared plus y squared. If you hadn't made this, if you hadn't squared both sides and you would have plugged in square root of x squared plus y squared, you would still square both things to get these x and y's. We should recognize this from Math 126, section 1.4. You did this section. This is just the equation of a circle. X squared plus y squared is equal to r squared. This is our radius squared, so that would make the radius 6. Any questions on this one?
When you decide to like do the plot the points, how many like variables does it matter?
You should plot. So the question was, if I'm doing plot the points, how many should you put in your chart? And I would say as many as you need to recognize what the pattern is. So like over on this last one, I picked 0, 1, -1, 2, -2. That was probably enough for me to see what the pattern was because it's a straight line. If you couldn't see from that, we could have done 3, -3, 4, -4, etc. Here, I just picked some angles until I got around to the 3rd quadrant. And once I got to the 3rd quadrant, I realized like, okay, this is just a set of points that are 6 away. So that ends up being a circle. But if you need more than that, feel free to do 10 or 12 or whatever you need until you recognize the shape. And in this section, the only shapes we're going to do are circles and lines. So you should end up with a circle or a line. Any other questions? Okay, let's do one more. And I gave it away. I shouldn't have given it away that I'm only doing circles and lines. This one's a little bit crazier. Let's graph r cosine of theta is equal to -2. All right. The last 2 examples, we only had our equations in terms of one variable. This one we have both r and theta. Now, if we think about making a chart of values for this example, it's not impossible, but it's really messy. I'll just say that it's really messy. So what this would entail is us picking a value for r and then solving this equation for cosine. Picking another value of r and then solving this equation for cosine. This is not a very simple equation. Imagine here if we plugged in r as 3, right? We divide both sides by 3. Now we get cosine of theta is equal to negative 2/3. We'd have to take inverse cosine of both sides. That is a ton of work, right? So sometimes this chart of values doesn't really make a lot of sense to use. And in that case, what we're going to do is convert to rectangular form. So you don't have to do the chart of values. All right, so help me out with this one from last class. This one should be a really quick conversion. Our cosine of theta is equal to what? X, yeah. So we get x is equal to -2. Now, if we look at this, this is a very simple equation compared to this with 2 variables and a trigonometric expression in it. So x is equal to -2. So we know what this looks like from our previous math classes. No matter what y is, x is equal to -2. If you need to make a chart of values at this point, you certainly can do that. But here's x is -2. No matter what y is, x is -2. So here's y is 0, x is -2. Here's y is 1, x is -2. Here's y is 2, x is -2. And we get a vertical line. Now, the interesting thing about this is that the alternate form in polar form is this r cosine of theta is equal to -2. So what that means, if we look at any point on this line, for example, I have this point up here, right? Here's theta, here's r. I realize my yellow is not showing up very well. Let me pick a different color. Okay, so here's another point on the line. Here's r, the distance from the pole out to the point, and here's theta. So it turns out that if we found r times cosine of theta, this would actually be equal to -2. If we did this for some other point on the line, so here's another point on the line, here's r, here's theta. If we plug this in, r times cosine of theta, we would also get -2. So it turns out that this actually simplifies really nicely, and it's kind of an interesting result here. Any questions on this one? Okay, so for our class, I gave you 3 examples here. We had a vertical line, a circle, and we had a non-vertical line, a line with a slope 1. I'm not going to do anything more complicated for our class. What I want to do now is just show you some slides of what other polar equations graphs may look like. And you don't need to know these for our class, but what you should recognize is later on in your math or physics or engineering or whatever career, if you see anything that looks similar to what I'm about to show you, you should have this aha moment like, oh yeah, that looks like one of those polar equations that Adrian mentioned. Let me look up those equations. Okay, so I'm going to show you some. You don't have to write these down. It's not on your homework. It's not on your quiz. It's not on your test, but I want you to be exposed to these. If you do want to check these out later, they're in your textbook. Okay, so these are all the different types of polar equations. And let me move this chart. Okay, so polar equations, we saw these 2 already. Okay, so if we have an equation that's theta is equal to some number, we end up with a line, and we have to remember we not only get the terminal ray of that angle, but we also get the opposite ray. This should make sense if we have an equation that's r cosine of theta, we know that's equivalent to x. So if we have r cosine of theta is equal to some number, we get a vertical line. In the same manner, if we have r sine of theta, which is equivalent to y, we get a horizontal line. Okay. So the other types of equations we saw was circles. Okay. So if we have something that's r is equal to a, this is a little example we saw, that one's pretty straightforward. That a radius is equal to some number, that's just a circle centered at the origin. Now, this is where it gets a little bit more complex on the next couple pages. If we have the polar equation, r is equal to plus or minus 2a cosine of theta or 2a sine of theta, it's a circle not centered on the origin. And I'm not going to go over the proofs of any of these or how we get those graphs, but again, I just want you to recognize later on in your math career, if you see something like this, you might think like, oh yeah, what was that polar form again? Here's where it gets even cooler. So here are some of the other shapes that polar equations can take on. So they're kind of heart-shaped, and around Valentine's Day, you know, you might have seen some post on Facebook or Instagram or something, the equation of a heart. They're actually just based in polar equations. So you can see these equations here are just r is equal to a plus or minus a cosine or sine of a. Here's a different, slightly different form and slightly different form, and these are the outcomes of the graphs. Okay, so again, what I want you to recognize is, should you see this later on in your math career, I just want you to have that aha moment. That's a polar equation. Let me figure out what polar equation represents that. These last ones are even cooler. We have some flowers. So we have a flower with 2 petals, 3 petals, and 4 petals. And even though these graphs are extremely complex, just looking at these graphs, these are not straight lines, not circles. If we look at the equations of these graphs, these equations are actually really simple. So, right, this one has 4 petals. That's kind of the most complex graph. The equation of this is just r is equal to a sine or cosine of 2 theta. Okay, so we have these really neat shapes that have some very simple equations in polar form that describe them. Okay, so again, I just want you to have this recall later on. If you were ever to come across these shapes in a class, you should say, that looks like something in polar form.